Let me introduce our next speaker. This is George Konidaris. George lives with one foot in both sides of academia and industry. In academia, he's the director of the Intelligent Robot Lab and is the John Savage Assistant Professor in the Department of Computer Science at Brown University. And in the industry side, he's the co-founder and chief roboticist of Real-Time Robotics. George has firsthand experience bridging the gap in research, taking an idea from his research lab all the way to the product that is now deployed in various positions or places today.
Thanks, James. You all can hear me. I can hear me echoing back, so good to see you. So first of all, I wanted to sort of put it as the title says Robotics at the factory floor. I can't show you any photos of factory floors because the companies that we work with have proprietary things happening. So I'm going to show you some. Occasionally, I'll show you like simulated pictures, but there won't be any kind of real factory floor pictures. They exist, I promise, but they're not ours. And the other thing I wanted to mention before I start is Real-Time Robotics. So we started we opened up in May 2017, sort of 3 of us at an incubator many moons ago, 4 of us at an incubator. Now we're 85 people in Boston in the Seaport, having a lot of fun, and all of the cool stuff that I'm going to show you is theirs, not mine. I'm just the sort of academic who shows up and everyone treats nicely like a sort of doddering grandfather. Really, it's the engineers and the research scientists that work with us who do all the fun and cool stuff. And if you're ever thinking of moving to Boston and joining a robot company, you should call us, because everyone is smiling. Smiling makes fun robots, which is happy to work. Okay, so where did this start? Well, I was an assistant professor at Duke in the fall of 2014 when I went for a fortuitous lunch with a computer architect. And he said, hey, I wonder if there's some sort of computer architect thing we could do with robotics, or any important problems that you might wish to solve. And I spent a lot of time thinking about motion planning. So he and I started a research project to see if we could build a specialized processor for motion planning. And if you fast forward a little bit, you'll get to this RxS paper in 2016, robot motion planning on a chip. And the exciting sort of headline takeaway piece from that was that we built sort of instantiated design of hardware processor on an FPGA that could do motion planning for a 6-degree of freedom over arm in less than 1 millisecond. Okay, so what we did at that conference is we showed all this. This is sort of a classic, robot research lab video. There's a robot. We sort of built a frame, and then we bought some stuff from like the local toy store. We bought some brightly colored blocks, and then we got some cardboard boxes. And then Sean, who ended up writing his PhD thesis on this question, Murray is going to show up and press the button. And the button was the signal to start planning. So you see there's no delay between when you press the button when the robot starts moving. And now the robot has sort of put the block away. After the plan, there's a motion plan. And then Sean would kind of move the obstacles around, and then there was a vision system that perceived the obstacles. And then he would press the red button, and then it would sort of make a plan in less than a millisecond, and the robot would start moving. Okay. So we were very excited by this. This felt like a really fun and exciting thing. It wasn't like a couple hundred milliseconds. It wasn't seconds for planning. It was instant. So we waited for Sean to get most of the way through his PhD, and then undergrad student worked with us to graduate. And in May 2017, we formed Real-Time, and we started to build a product based on this thing. And part of what I want to talk to you about today is all the things that I wish I'd known when we started, because I'm a lifelong academic, and therefore I didn't understand capitalism at all, or like how industry works. And so we had to learn some lessons. Okay, so the first lesson that we had to learn was about how you build products. So this was the first version of our product. We were very excited about this. It looked like a little GPU that sat in a box, and it came with a C++ driver, which we felt was very well documented. So we were going to sell these things. We imagined that we would put them on a website, and then people would come along and they'd click add to cart, and they'd buy our motion planning processor, and they'd have a C++ interface, and it would motion plan. Of course, you had to like interface perception and all that stuff, but people knew how to do that, right? So, so our theory was that we were going to sell this chip, and we made demo videos like this, which I still kind of find funny. So this is a Planet robot and 3 universal robots, which we borrowed from Mass Robotics, in a workspace where their targets are generated randomly at runtime, and they kind of are motion planning around each other. And they can kind of do that with no delay, and they can kind of move at full robot speed. Okay, so in academia, if you were to show a video like this, then you just kind of win, right? Like everyone's like, wow, you know, these robots, there's no delay, they're moving around, they're not smacking into each other, motion plan is solved, we can all go home, and you know, winage, everyone is just feel pleased, very, very happy. And I still actually personally, as an academic, still feel happy when I see a video like this. This makes me happy. This is the kind of thing that I would like to see out of life. Okay, but the first lesson is capitalism is not like academia. Okay. So in academia, what we imagine is that everyone is going to go build these super smart, really cool robots that look like this. This is a DR, some kind of German space robot, is a way to think about it. But everyone is trying to make, you know, generally intelligent, super flexible robots that can go out there in the world, and everyone understands that that's the goal, and we all understand that there's a complicated stack involved, but we all have master grasp, and we're going to plug everything together, and we're working very hard to make that happen. And in almost every single actually deployed robot that has more than 4 or 5 degrees of freedom operates in an environment like this. So this is, I just stole this off the internet. This is a picture of a robot. Robots working in an automotive factory. So what's happening here is you have massive robots running this very, very very tightly orchestrated sort of ballet, right, where there are no degrees of freedom in this setup, right? That robot, that car piece is brought to the exact same spot, down to the millimeter. It's a very expensive factory because it's brought to that spot. And then those robots run in an open loop, roughly speaking. Mostly they don't have any sensors. Mostly they're just running in an open loop, and they're doing very, very precise motions at very high speed, because a couple of things matter. Reliability matters. Okay, so if you happen to drive a car, you would like to believe that the welds happen in the same place on the car for all the cars, so you don't need to worry that your personal car is going to fall apart. That is a big, big deal. Another one is that the companies making these things really care about how long it takes to get them out the factory. So that's why an industrial robot, you know, one of the selling points is that it's got sub-millimeter repeatability, and it's very, very fast. Okay, so we just sort of thought we would, you know, claim to the world, hey, we've got this motion planning solution. You don't need to build factories like this anymore. You can just, you know, everything can just roll into whatever location it is. You'll plug in your perception system. You'll perceive the world. Tell us where to go. We'll go there, and then like factories will be different, and everything will be wonderful. And that's not how that works at all. Everyone we spoke to was like, hey, that's a cool robot demo. We would like to buy one of your processors for our R&D department so that the kind of geeks in the R&D thing can play with it, but it never got any further than that. And one of the reasons why, one of the other lessons that we learned is that there's a difference in robotics between, actually this is true for most fields, but it's especially acute in robotics, between what's called a horizontal and what's called a vertical. So vertical means you have to build a complete product from the bottom to the top. And then you have a deployable unit of the thing you can sell to like an end user. And horizontal means that you build a component that lots and lots and lots of vertical products are going to have in there. Okay, so to show you the difference, a Roomba is a vertical. You build the whole Roomba, and you get to control everything that goes in the Roomba, and you get to, so there's some responsibilities here. You're going to have to master everything that takes to build the Roomba, and that's a lot. On the plus side, you get to choose everything about inside the Roomba. You don't have to fight with anyone to see if, you know, you prefer their stack. And no one can say no to you except the customer. So you can build a Roomba and go into the market, and if your Roomba is better than whatever exists in the world, then you can sell some. It's the same thing for like someone selling a modem. You know, you just sell a modem and you get other modems, and it's a complete thing. A horizontal is more like what we built. Okay, it's a processor. It's got to live inside a product, but we don't get to build the product. Someone else gets to build the product. Okay, so it's like owning the Wi-Fi chip or something like that. The upside is you've developed a new technology, you've got a fundamentally new technical thing, you can be very narrow focused, but you don't get to build the product. Okay, so the downside of a horizontal is that someone else has to succeed before you succeed. Okay, so we build this thing, this processor, we send it out into the world, we say, hey everyone, you can sell thousands of robots, 100,000 robots with a motion plan. Okay, but someone's got to go build a robot system that uses motion plan to do something useful before we get to sell 100,000 units. Okay. So that's really hard. So you have to go out into the world and you have to sort of think, okay, well, we can do two things. One thing is we can go to startups who need motion planning. We can sell our process to those startups, and we do that to a lot of startups. And we hope that we fit in their stack because they've probably already got a stack. And they're going to argue with us about what they need, and they can just say no anytime because they just don't want it. Right? Like the engineers don't like hardware, or they don't feel like doing things your way, or there's some detail about your process that annoys them. They can just say no, and then you're done. Right? Or we can go into existing large corporations that have hundreds of thousands of robots deployed. We can say we can improve your process better, but that's very hard to do with a horizontal. So we thought, well, we're going to do the big company thing. There's hundreds of thousands of robots that are out there in the world. They're being constantly repurposed. Let's go find some large companies that use them already. So the next lesson is know your market, which everyone has told you already many, many times. And the reason everyone tells you that is because you have to know your market. There's just no way around it. And in academia, your market means like your reviewers. Okay, that's your market. Maybe it's the best paper committee if you're very lucky. But in real life, the market's who's going to write the check. Not who's going to use the product, who's going to write the check. Because in capitalism, the win happens when the check hits your bank account. Doesn't matter how many people like it, how many people share your videos, how many people comment, how many people think you're cool or say hi to you at a conference. It happens when the check hits the bank account. Okay, so, and most of these reports are proprietary, so I can't show them to you, but I found one on the internet, which looks at the number of robots, percentage of industrial robots in each segment. Okay, this is from McKinsey. So it says 20% automotive, 9% machinery integrators, that's also automotive, and 20% electronics and 20% pharma. And one thing to know, if you know your market, is that electronics and pharma, these are sort of typically these kind of delta robots. They're more Cartesian, they sort of hang off the ceiling and they go up and down. They don't need motion planning, so we don't think about it. So there's other, and this is a lot of warehouse stuff is happening and that's growing and that's exciting. But mostly, for 6 and 73 freedom robot arms, it's in automotive. Okay, so 40% of the robots sold are what you and I were thinking articulated on. And more than half of them, 29 out of 40%, is in automotive. Okay. So when we spoke, and now there's some challenges here if you're going to go speak to a well-established large number of robot kind of market like automotive. Okay, one of them is you have to go figure out who they are, talk to them, spend a lot of time. You spend more than a year just talking to them, just figuring out what their lives were like. But you also need to understand what they care about. And so, you know, one of the things that we found is that if you talk to them and you look at their automotive automation costs, actually only like 19% is the robot arm. There's a lot in what they call operating costs, which is mostly programming and application software. Okay, so there's a big opportunity there to say, okay, actually, cheaper robot arms don't matter that much to them. What matters to them is how fast they can get these things programmed. So that felt like an opportunity for us. So then we decided to get to know those customers really, really, really well. So lesson number 4 is know your customers really, really, really well. And it turns out that the way that automotives work is not that they install ROS and then they open up Harvest and then they program the way that we program things. It's that actually there's a kind of intermediate type of person called an integrator. So there's what is called an end user, that's like Ford or Toyota or BMW or something like that. That's the automotive. And then there's a robot arm manufacturer like ABB or KUKA, and then there's someone called an integrator. And those companies hire an integrator. Integrator shows up and builds a work cell. Okay, so that's kind of what these are sort of examples of what a work cell will kind of look like in that setting. And it's mostly mechanical engineering. Okay, so the integrators are very, very smart people, but they're mechanical engineers. They're not computer scientists. They're not used to programming. Mostly, they're used to getting everything to plug in together, to running it in a big mechanical engineering simulator, and then just kind of, you know, doing throughput stuff. And then the end part where they have to decide where the robot goes, they just kind of program it by hand. Okay. So we have to understand how to reach those people, and it's not giving them a C++ API, it's not giving them a ROS API, it's not doing anything that's programming ready. It's building a set of tools around our processor and our underlying motion planning technology that look like what they're used to looking like. So the end iteration of our product actually looks much more like this. This is actually an old version. Now it's just an industrial controller. It's a complete machine that plugs into an industrial work cell unit that your robots plug into using industrial CAT. And then you can send PLC commands because they really like using PLC programs for some reason. That's just what they know. And so we present a PLC API to them, and they tell us where they want the endpoint of the robot to go. And we handle everything. We handle motion generation, we handle timing, we handle collision detection, we handle deconfliction. You can plug up to 12 robots into this box and just tell them where you want the sort of end effects to go, and we'll kind of make that happen. And you know, things like you can plug in industrial vision systems in, and it just kind of all works, right? So it's focused on what the integrator needs. So just to give you some examples of kind of what our software looks like, here's an example of kind of thing that we sort of building up a motion planning thing. Our software, at least at this time, was built on obviously roadmaps. We thought we would auto-generate those, because who wants to specify them? It turns out integrators really want to specify them. They really want to know in advance what the robot movements is going to look like. So this is kind of like, you know, how we would say if you wanted to do spot welding on a point, and then you wanted to generate motion plans, we kind of build up the sweat point for those motion plans. Here's a sort of zoom into something more recent, kind of dark, but you can see there's a chassis and there's a spot welding robot, and it needs to make a motion like that. We need space to be able to spot weld in a point on the robot body, on the car body. So we build software that looks like that. One other thing to say, and a lot of people have said this before, is that product, okay, because now you're shipping product. You're not shipping ideas, code, or videos, you're shipping product. And product means reliability. Okay, so I can't give you exact numbers, but it is millions of dollars an hour for an industrial robot maker's factory line to go down. Okay.
The battery died.
The battery died? You know, that's a bummer. Can I just now I'm going to fill out the young. Okay, let's do it. Does that work? Okay. So it's like millions of dollars an hour for an industrial robot manufacturer's line to go down. Okay, they ship like an insane number of cars from each of those things. So you really can't break. Also, this is not a picture from real factory. I just found it on Google. These robots typically weigh up to 900 kilograms, and they move up to 600 degrees a second. They cannot collide. Not 1 out of 100, not 1 out of 1,000, not 1 out of 10,000 times. They cannot collide. Okay. So what you need to do, and what we did, was we really geared up on professional engineering. Okay, so common failure mode for startups that come out of academia is too many PhDs doing PhD things. PhDs are wonderful, PhDs are smart, PhDs are brilliant. What you actually need is professional engineering processes, and our engineers are amazing. I cannot do what they do. They're really fantastic in every way, but you need like a 5-to-1 engineer to PhD ratio at least to be able to produce a product that you believe you can roll out to the world. Okay, lesson number 6, last lesson for now, is that you need to innovate all the way to ROI. So ROI means return on investment. Most things that are not automated with robots are not automated, haven't been failed to automate because we just can't do the thing. We can do the thing, but we can't do it in many cases as effectively as a human can do it. Can't do it as cheaply as a human can do it, or as quickly as a human can do it. Okay, so in our case, we couldn't just say, hey, we can do stuff better. Here's some technology, you guys figure out how to use it. We had to take the work all the way up to the point where we could make clear, quantitative ROI projection. We could say, you're going to save this much money. It's going to cost you this much money. It's going to take you this long to switch your line. And then you're going to be able to save this much money per instance. And this is going to pay itself off in this long. In order to be able to get the person writing the check, because remember, that's your audience, not the guy doing the engineering. The person writing the check is supposed to be the audience. Those people to agree. And if you're working in a field in which there are a lot of deployed robots, they are conservative. They don't want to break things. Things are currently working. You really need to get over a fairly large company. So where we actually found our kind of killer first breakthrough app was in part from this video, which we kind of made just to show off in the beginning. After we built the NPA, we thought, okay, we have multiple robots picking up these sockets, generating the motion at runtime, and then I'm like, hey, Sean, just stick your arm in there. We'll have 2 robots at the same time because that's cooler than 1 robot. And Sean, stick your arm in there and the motion plan around your arm. Wouldn't that be fun? And we released this video, and actually we noticed that a lot of those companies were kind of most interested in that video. And it turns out that it's because Most of their use cases where they have multiple robots deployed in a work cell is where their major pain point is. For a single robot in an automotive work cell, they're like, okay, I'll just hand program the trajectory. Everything's the same anyway, so it's kind of all fun. But when they have multiple robots in a work cell, there's always process variation. And some core integrator has to sit there and design, it's like a ballet of a bunch of blind ballerinas. They have to design a bunch of trajectories, do the timing, make everything work at the same time and not smashing into itself. And they want as many robots in the work cell as they can get, because it takes time to move the chassis from one place to another place. Okay, so what they do is they hand design these things, and then they add what they call interlocks, which are like zones where only one robot's allowed at the same time. And that's the kind of safety mechanism, because there's always process variation. So what we show is we just produce a simple video that says, okay, if you have a single robot, like doing pick and place up there on the left, it takes a long time. And if you have two robots but you have interlocks, like we put an interlock above that, then you can increase your throughput, but only by 14%. And that's actually kind of a typical number. Now remember, the cost of the robot's small compared to the cost of the work cell. Okay, so they don't mind buying an extra robot, but 14% is not a big win. But if you do the real-time thing where the robots just plan around each other at runtime, you can get a 75% increase in throughput. It's not 100% because there's interference, but you get a 75% increase in throughput, and the programming happens just instantly. You just tell the robots where to put their end effects. And that's the thing that got everyone to buy it. So just to show you a sort of cartoon of what that looks like in real life, I'll show you the real thing. This is an industrial robot work cell simulated in our software. We've got 9 robots in it. And there's some welding going on. And what you'd like to do is have those 9 robots all move simultaneously without having to design any interlocks or anything like that. So that's what our software is able to do with 0 latency and 0 delay. And that's where the kind of really big win comes in. That's where an industrial automaker, a large industrial automaker, is willing to say, okay, we could shut down our line for a day or two to swap out, or at least begin trials. And it's like a 3-year thing to get on the line of an industrial automaker because it's so expensive and their reliability requirements are so high. But this kind of demo is what allowed them to say, okay, fine, we're gonna go for it. One more thing, of course, you never take a single bet if you're horizontal like us. So we have a couple of other things happening. I've talked about automotive. This is an example of the same thing happening in palletizing. So this is with Yaskawa. These blue robots, Yaskawa robots are blue, nice fetching blue. So this is a palletizing situation, and we're just using Yaskawa boxes here, but they're being put onto a pallet. And the robots are moving in the same space and they're motion planning around each other. And they have to do motion planning because the boxes that come in are variable size and need to be placed in a kind of variable way on the pallet. Okay. And so this is a case where you could do multi-robot deconfliction, real-time robot motion planning, and all that sort of stuff in a relatively kind of well-contained application that feels a bit more like a vertical. Okay, I think I'm out of time. So that's all I got for now. Let me leave you with some robot videos. These are all public ones that I can show you, but there are actually real robot videos. So, great. Any questions?
Do you have any questions for the speaker?
So in the welding scenario, you're doing real-time planning on the fly, but does it end up just producing the same plan over and over again because of the constraints of the environment?
Yeah, often it does, but it depends on the other robots, right? So when there's a smaller number of robots, it does. But when there's a larger number of robots and there's, they're all moving around at different times, then they tend to motion. Then it's often the case that the direct route is blocked, and you kind of go around or something.
So it seems like you went under a pretty big pivot. How far along were you in your company's growth? Like how many employees did you have? Like where were you at when you kind of decided you couldn't be all horizontal? So
I'm not sure. I wouldn't quite phrase it as a pivot because we still make the same thing, but it was an evolution in the sophistication of our understanding of the thing. It's not like we made a different thing. We're making the same thing, but So I would say it was kind of mid to late 2018 when we realized we need to write a ton of software around this stuff. And kind of through 2019, we produced the first version of our software, and the second version is actually going to get launched at Automate in a few more months. So, so that's been one reason, is that we've been sort of iterating as we go. The things have taken a little while. The other one is just that, you know, we are in constant engagement with these very large companies, and they're not fast, and the stuff that you have to show to them for them to let you on the floor is a lot. But I would, in my head, I've got kind of 3 changes. You know, I guess it was the first one with the processor, the second one where we just thought we'd make some supporting software around it, and the third one where we really understood how that had to be structured and who we needed to target. And the last one was, yeah, I would say mid to late 2019.
Yeah, it's very interesting to see that not many power robot. And how do you compare with the traditional system integration that generate time with overall cycle time?
Okay, so my understanding, and take this with a grain of salt because I'm trying to remember this offhand. Traditional system integrators had a hard time getting above 6 robots in a work cell, and it would take them up to 13 weeks to do the programming for that, and with our system it took less than 2 weeks. So there's a productivity difference. And then, if I remember right, they got about 25% extra throughput for each new robot in a real setting, and we got them to more like 60 to 70%. So there was a measurable kind of forever improvement in that the robots would just act faster, summed over the lifetime of the robot, which is a big ROI thing, and then there was a programming cost reduction as well.
Was simulation that programming generated with both wrongly repeated or that one was just like your live demo randomly motion generated?
The motions are generated online.
And how can you always the cycle
Oh, yeah, it's not fixed anymore. So you have to, but it wasn't fixed before either, because, you know, the interlocks existed because there was process variation. And as soon as you need an interlock, it's going to be the case that sometimes one robot's in it and the other robot's trying to get in it, and there's some delay, and then that delay causes further, you know, so it's the process time is no longer quite so predictable, but you can run it many times and average it. But it wasn't predictable anymore anyway after 2 or 3 robots.
Thank you very much.
Last question.
Do you think you can take this idea about vertical versus horizontal like back to the academic context, where you work on something that is supposed to make a lot of robots a little better? You don't succeed as well, you actually make a lot of real robots better with it?
Yeah, so I think that's right. Although the notion of succeed in robotics is different, in academia is different. Succeed means like get cited a lot of times, maybe get a best paper, or people remember your name. And so it's definitely the case that that's happened a lot of times where someone has, you know, invented a new algorithm that maybe people don't ever deploy it, but they recognize as the state of the art or something like that. And actually, I think in academia we're geared towards horizontal. We're geared towards a narrow piece of technology that, you know, that we want to make better, that lives inside a nicely defined box, like motion planning, this configuration code. And yeah, that's right. If you want to do stuff in real life, you have to think about it. So I mean, there is a question of integration. There are academics who are all about integration. It's just it's hard to think about scientifically, to like generalize over instances. Whereas if you're building one specific thing, you can understand the best way to integrate that. It's kind of better practice in the single thing.
Let's thank our speaker one last time.
Thank you.